can this, I'll kill this here. How can this happen? Those password hashes are actually the current password and the last two passwords. So why are there 3 passwords stored on this key? The idea is that there is an enterprise version of this key, which is much better. This is for the big companies which need really, really good security. And in those companies, you always have this stupid rule or this naughty rule that says every 30 days you need to change your password. And so to make sure that when you change your password, you don't use the same password again, or the password from last month, or the one from the month before, we need to store that password somewhere, or at least the password hash, a SHA-1 hash. So in the enterprise version of the software, they store the last 3 passwords somewhere on the key, but the amazing thing is they stored it on a place which is readable by anybody. You don't need to authenticate before you can access to those hashes, right? I never typed a password. I just plugged the key in, I found the password hash, I brute forced it. So if it was any of your key, I could have taken it and found your password hash. So if you want to do some conspiracy theory, you could say the NSA didn't want the key to be too secure. I have another theory. I think this was the marketing department. The engineers made this really good hardware. They scratched off all the references on the chips. This was really unbreakable. And then marketing came and says, we need something more so we can sell it to more people. We need this funny function that you cannot use the same passwords again. And they programmed it in 2 nights or whatever, and this is what came out. So what they should have done is, the best thing, of course, would have been to do the validation of the password also on the processor on the USB key. So when you try to change the password, you send the candidate new password to the USB key. It will check in its EEPROM somewhere if this is a valid password or not, and then it would answer OK or not. Or at least if it's done only by the Windows software, it should store it somewhere that you can only access once you have typed the password or put your finger on the key. That would have been the minimum that they could have done. But they were very reactive. We had a phone call with the CTO the same day, and the same week they issued a patch and the thing was fixed. So this is a story of the past. Okay, that was the first example. Now, if you think what they actually programmed, these guys from marketing or whoever it was, it's something that records every password that you type, so it knows the last passwords. So this is really a keylogger. They have invented the keylogger, but they made a bad keylogger because everybody can read out the password hashes. This is a second example. This is called the eCapsule private safe. I have one of these too. So what this software does, this is something that was discussed in the last talk. No, that was in another talk down there about deniable cryptography. You have some data which is encrypted and you don't want to show it to somebody. So say you have to cross a border and there's a guy at the border who asks you if you have something illegal on your USB stick, and you want to tell him, no, I don't have anything illegal, and you type a password and the stick opens up and you see vacation photographs or whatever, which is all fine, and you can get through the border, for example. So for this software has 4 different passwords. The first password will allow you to administrate the whole thing, create new passwords or change the existing passwords. The public password will give you access to one part of the documents, which could be your vacation photographs, and then the private password gives access to another part of the documents, which could be whatever you're just going to bring to the guys of WikiLeaks or whatever. I don't know what your private business is, but things you don't want to show to everybody. And then the 4th password, this is very important. There's a panic password. You type this one in, and it shows an empty folder. And you cannot make a difference between a folder that was always empty or which has just been emptied now because you typed that password. So when somebody asks you to type a password, you just say, OK. And you can choose, you want to have vacation photographs, you want to have your private stuff, or you want to have an empty screen. This is really, sounds very useful. So how does this work? It stores all your data in 2 files. I think we can look at those files somewhere on this U3 system, I think. It's in documents. There's different applications on that U3 stick. One is private safe. And it has safe.eck and safe.efs. EFS is the file system which is encrypted with this software, and ECK is some sort of control block. I'll show you on the screen, you'll see how it looks like. It looks like this, so it's a short file with some binary data in there, and if you look at it, this data is made of 4 different blocks. And every block starts with something very distinctive. There is a ASCII 0 here, it's 30 here, and then there is an ASCII 1 here, and an ASCII 2 here, and an ASCII 3 here. I cut the last part, but it's the same size of block. The last 3 blocks have the same size. The first block is a little bit bigger. So there are 4 blocks in that control file, and if you do some reverse engineering, if you go into the code, into the debugger step by step, you'll find out how those blocks are encrypted. You find out that what they use is AES 256, which is very safe, in CTS mode, which is a mode that is not used very often, where you don't need to do padding. It's very much like CBC, but you don't need to do padding. So I guess it's for the lazy people who don't want to pad their data. So you need a 256-bit key, and that key is the SHA-256 hash of your password. So when you type a password, this will be hashed with SHA-256, and then this will be the key for encrypting your data. And the encryption algorithm also needs an initialization vector, something to initialize everything. It's like a salt in a password hash. And what they take as a random initialization vector is another hash. It's the RIPE MD160 hash of your password. So it also depends on your password. And then if you look at once you find out this, you can decrypt the block by hand, actually. And if you decrypt it, you can see what it's in there. And so we're going to try to do that by hand. Fortunately, sorry, I've done that before. So I've copied the content of that on my Linux partition, so they don't get into each other's way, but we have the same files that we saw before. So if we go into private safe, we can see this control block. Here it is all encrypted. And now we're going to do all this encryption I told you before. I've done that the last half hour, so I'm sure it's going to be easier now. So what we do, we set the password to be admin PW. That's the password I have as the administrator password. And then I'm going to take my encrypted control file. I'll pipe it into OpenSSL with AES 256. The key of AES 256 will be, again, the password piped into OpenSSL to do SHA-256. And the IV is, again, the password piped into OpenSSL through RIPE MD160, which is too long, so we have to cut it, and we'd only take the first 32 bytes. We're very, very happy to have OpenSSL because it would be a pain to do all of that by hand or to program it, right? So we're going to try with admin PW. And now we see it has decrypted the first block of this file. And in this block, we find the username, and we see 0 has the password admin PW, 1 has the password public PW, 2 has private, 3 has X. X is my panic password. Remember, this is the panic password. I'll use it later. It is only 1 character long, so when I type it and you see only stars, you'll know that must be the panic password because the other ones are much longer. So if I used the admin password, I'll see the first block. If I use any of the other passwords, I can try. Oops, I'm sorry. There it decrypted the part about the public information. It only says the same thing, Philippe hardware software. For some reason, it's always the same plain text. I have no idea what this does, but it's enough to find the bug. You don't have to understand why the bug is there. So if I have the private password, I get the next block. And if I give my panic password, it should decrypt the last part of the file. Here we see Philippe hardware software. So we know now how this thing works. Now this is no big secret, right? I mean, we've reverse engineered. We know it does AES encryption. So what can we do now that we found out about this? What could be the trick? What could be applied? Oops. I'm sorry for all that switching. So this is what you just did by hand. This is the blocks if you decrypt them clearly. And this is what we could do. See, we have this file which has those different blocks. So maybe we could try to exchange the blocks. We just cut the whole key block of the public password and the one of the